Morning, everybody. So I'm going to go through the 2014 test the same way I did with the 2015. I'll do one video at a time per question so you can kind of watch short ones rather than having too long. This is going to take us about up to the test on May 12th. I am going to continue to post other resources if you want more optional work, but I think it's nice to see questions that are me explaining them and are topics that I know that are things that could be tested and similar to what you may see. So we're going to start with question number 3. I'm sticking with all non-calculator questions, even though you will be able to use a calculator on the test on the 12th. They have said they are not going to do questions that are extremely calculator active, more like a convenience than anything else. So here's question 3. So I do want to just kind of make some comments about what I did at the beginning, because I actually started with this. Anytime they give me a problem where they have a function defined by an integral, I'm immediately going to make this little list up top. So here's my original integral that they gave me. What I know is if I derive it, I'm going to get what I started with. That's we call it the second fundamental theorem of calculus. If you derive an integral, you get what you started with. The only change is this variable x becomes the variable of f. So we know that g prime equals f. And then from there, we know that if we derive again, g double prime is equivalent to f prime. So that's kind of like my go-to list that I'm going to look at. So part A wants to know g of 3. G of 3 means that I'm going to put 3 as the upper boundary of this integral. So what it's actually asking me for is area under a curve. So you can see my geometry work up here. I'm going from -3 to +3. So from -3 to 2, you have this big triangle. So I put my work off to the side, 1/2 base times height, and got an area of 10. Now from 2 to 3, we just have this very small triangle. It is underneath the axis, which is why I wrote it as negative. And I put my work down here, 1/2 base times height. The height goes from the axis down to -2. And I know that because I know the slope of that line. So I know it's going down 2 for every one it's going over. So that one would have an area of 1, but it is negative because it's where it's located. So my final answer there for A would be 9, 10 plus -1. They were very minimal as far as work and answers. All you needed was the answer 9, no matter how much work you showed, and you get a point. So back to the question, part B wanted to know what intervals between -5 and 4 would you have an increasing concave down graph. So here's what I started with. I just kind of wrote down, what does it mean to be increasing? What does it mean to be concave down? So to be increasing, the first derivative has to be positive or bigger than 0. And the second derivative, to be concave down, would have to be negative or less than 0. So I kind of made that little list. So what I'm looking for, g prime is going to be represented by just plain old f. So if I want that to be positive, I'm looking for a graph that's above the x-axis because that would be positive. And then for g double prime, that's going to be the slope of f because g double prime is equivalent to f prime. F prime is your derivative of f, so it's slope. So in order to have a negative f prime, you would need a negative slope up here. So I'm looking for intervals where it's above the x-axis, but with a negative slope. That happens at the very beginning, from -5 to -3. And then it happens again from 0 to 2. And your answers are all x values. So that was kind of my work. My explanation is what I'm looking for. And then over here, I wrote my final answer. You can put parentheses around this because they call them an open interval. You can also write it with inequality symbols. But as long as you have those two intervals and you explained what you were looking for in words or symbols, I believe this was worth 2 points. Yeah. 1 point for your answers, -5 to -3 and 0 to 2. And then 1 point because of what you're looking for. And there's a lot of ways to write that. Part C wanted to know if we have this h function and it wanted to derive it. This is a quotient rule. That's the first thing I wrote down when I started this one. I wrote a little QR for quotient rule. So here's bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. I need to put 3 in. So you can see my work over here. I put a 3 in for x. This one's g prime of 3. G prime of 3 is the same as saying what is f of 3. So if I go over to 3 on my graph, f of 3 is down here at -2. So it's the actual y value of that point. So I have 5 times 3 times -2 minus g of 3 we actually found in part A. G of 3 was 9 times 5. So again, you will be able to use a calculator, so I wouldn't get bogged down with the arithmetic. You end up with a -30 minus 45 or -75. And then the bottom, when you put 3 in, you get 15 squared, which is 225. You do not have to simplify. They would accept that answer. They would accept -1/3, -0.333, as long as you go 3 decimal places. And here's what they did as far as points. They gave 2 points for the derivative. Usually quotient rules, they will give 2 points just because it's a little more complex rule. And then 1 point for the answer. And again, here's all these acceptable answers that they would take. And then part D now has this p function, and p is a chain rule. It's kind of like a semi-generic chain rule. So it's f of x squared minus x. So to derive a chain rule, you take the derivative of the outer function, keeping the inside the same, times the derivative of what's inside. So here's what that actually looks like. So you would have f prime of x squared minus x times the derivative of what's inside, which is 2x minus 1. You're putting a negative 1 in everywhere you see x. So put negative 1 in here, you get f prime of 2, times when you put negative 1 in here, you get 2 times negative 1 minus 1, which is negative 3. F prime of 2 is the same as figuring out the slope of f at 2. So when you go here, it's saying, what is the slope of this segment at 2? It has a slope you could count if you want. You can use point slope or a slope formula. You get a slope of negative 2. So you have negative 2 times negative 3, which is 6. I actually realized I did more than I needed to do. I started writing a tangent line equation. They didn't need that. Now, if you do extra work and it's not needed, you used up some time, but it won't penalize you. So as far as the scoring, they gave 2 points for the derivative, again, probably because it's a chain rule and it's a little more complex, and then 1 point for the final answer of 6. So that's question 3, really common. It's like a curve analysis question. So it uses things from chapter 2 with derivative rules, chapter 3 with curve analysis, and even a little bit of chapter 4 when you talk about area under a curve and integration. So go ahead and score yourself out of 9, see how you did, and then keep track of that one. I'm going to go over question 4 next, so you have a chance to grade that one as well.